7.2 properties of exponential functions, so more graphing. Now, in this intro, the graphs, this would be considered the parent function, 2 raised to the x. Now, the parent function for exponential functions will all look a little bit different. The one thing that will be the same in every parent function is this point right here, 0, 1. The reason why they look different is because we have this base 2. So in this case, we have a base of 2. So in the red is my parent function, if you look right here. And this 3 is going to be a transformation. In this case, the 3 will stretch it. Now, the same for every single type of graph. If it's multiplying, it would stretch. If there was a negative, it would flip. If there was an x adding or subtracting, that would move it left or right. And if there was a number outside, it moves it up and down. The only difference is for every single graph, what that represents on the graph is a little bit different. So now we're going to be graphing the parent function and the original. So this is the only time I'm going to graph both the parent function and the actual transformation graph. So kind of like up there. So my parent function is 3 to the x. That's going to be this right here. My transformation function is the negative 1/3. 3 times 3 to the x power. Now the first thing, when you're looking at this number, if it moves left and right, that's the number that should be in the center of your graph. So I do not move left or right here, so I'm going to plug in 0. Now for all of my exponential functions, I'm going to plug in 2 numbers to the left and 2 numbers to the right of that original problem. And then you actually plug them in. So when you're doing your table, you can use your graphing calculator. Make sure you put into your y equals. Go to second graph, go to your table. One thing I do want to show you, you can have your answers in decimal. It might be easier to graph, but I want to show you how it kind of has this pattern for every parent function. Now when you plug 0 into the equation, you get 1. Plug 1 into the equation, you get 2. Plug 2 into the equation, you get 9. Now remember, negative exponents actually just flip the fraction. So 3 to the negative 1 is 1/3. 3 to the negative 2 is 1/9. See how they match right here? Now with every transformation, it gets a little bit different here. So this is what, once we plug them in, this is what we have. So if I plug negative 2, that gives me to 1/9, and then negative 1/3 times 1/9 is negative 127. And now plot these points. When you are doing this, you're going to have an asymptote for all of them. And even if it doesn't ask it, I want you to make sure to write down your asymptote and your domain and range. So for both of these, I have an asymptote that would be at x equals 0. I have an asymptote at x equals 0. And always represent your asymptote with a dotted line on your graph. So now if you plot these points, and these are your 2 parent functions and your transformation graph. Now if you see, I added a point to my transformation graph because I know 3, negative 9 would also fit. So when I'm looking at this, I'm only going to be doing my domain and range and asymptote for my actual new equation. My domain can be all your numbers. Any number can put into that graph, any number at all. My range here, because of that flip, because of that negative out in front, all numbers would have to be less than 0. And that's why we have that asymptote at x equals 0, because there's no way that we will ever get any positive numbers here. There's not even close to an option because there's no number we can plug in to get a positive number because of the negative out in front. So you should flip that page and try B by yourself. You do not have to graph the parent function. That was just me showing you what it kind of looks like, but you do not have to graph the parent function each time. So now I'm looking at this. Here's my parent function. Sometimes it helps people. You do not have to do this. To box in what your parent function is. That's my parent function. So that -4 right next to the x, that does something to it. And just like every other single question that we've had with graphing, adding, subtracting with the x is going to move it to the opposite. So in this case, it's going to move right 4. So when I find out my table, since it moves right 4, I'm going to plug in a positive 4, and that should be in the middle of your table. Left and right, that should always tell you we're in the middle of the table. So then I'm going to plot 2 points on the left of that and 2 points on the right of that. Again, this is where you can plug into your graphing calculator to figure out your table, or else you can just plot those points in and then do it mathematically in your head. And then you should plot those points. When you are doing these, you should make sure to include your asymptote. There is an asymptote, and it's going to still be at x equals 0. this right here would be your asymptote here, because it will never cross it. You cannot plug any number in there to get a negative number out. So my domain here, I can plug any number I want into that. My range here, I will never go below that dotted line, because that's what an asymptote means. It will never cross it. So y has to be greater, not equal to, but greater than 0. My asymptote will be at x equals 0, because its x values are the horizontal line, so that's horizontal. So you should try the next one by yourself. Be aware that because of this 20 right here, for this next one that you're going to try yourself, you're probably going to count by tens for the y value. In words, it says, how does this compare to the parent function? So right here, I'm going to actually, so right here is my parent function. Anything raised to the x power. So really, there's only one thing for this first one. The x moves it left and right. The x is always opposite. So in this case, the only thing that I have here is left 2. I'm just going to give you also, this right here is my parent function. So the decay and growth part is not what changes the actual transformation. So I'm going to have a stretch of 5 because I'm multiplying by this 5. This also is on the outside. It's not written little with the x, so let's move it up 5. What actually moves up 5? Well, think about that dotted line. We have not had a plus or minus of any number yet. It's always been 0. That's that asymptote. When I move up 5, that moves that asymptote up 5. So these are the same thing that we just went through. Numbers with the x move it left or right. Number outside moves it up and down. The a value would have a stretch or compress or reflect. Again, you can say shrink for that too. So if I look at problem 3, actually you can look at problem 3, but we're going to be doing problem 3 in class. So you can skip it for right now. And both these two questions have to do with problem 3, so we're going to keep on keeping on. And up until now, we have worked with rational bases, b. However, we have an exponential function for the irrational base. One important irrational base is the number e. E, kind of like pi. Pi goes on forever, it does not repeat, and this is the same thing as e. E is called a natural base for exponential functions, where the base is e. These functions are used for continuous growth or decay. They have the same properties, the exact same properties that we've been dealing with, except now it's just with the base e. So if you look at your graphing calculator, so these first questions are on your graphing calculator. If you look at your graphing calculator, which you should have one, and you should have one in your backpack or someplace, or maybe you can pull it up, there is a e right when you find the button that looks like this, and there should be a little e to the x for your second key. So for this problem, I want you to evaluate this. So all you have to do is push the second key and then this button, and it should pop up with the E in a little box. In this case, you would put 3 in, and then you should check to make sure that your answer should be 20.0855. We always want you to round up 4 decimal spots. So then I want you to try e to the 8th power. Try that by yourself. In the last lesson, we talked about compounded annually. Well, this is what we would have, a new equation, if we are continuously compounding, meaning every single day we are taking that interest into the information instead of doing it at the end of the year. And that equation is going to look like this. So just like before, we start with this. We have a principal for whatever we start with, and then every single continuously compounded has this e value in it. And then we have our time times our rate. So it's never going to be plus or minus. It should always be a positive thing because it's always going to be a growth. So in this case, we would want to have this equation. Make sure you write that down. So suppose you want a contest at the start of 5th grade because you're so amazing. You deposited $3,000. That would be your P. It pays a 5%. That's the same thing as 0.05. And then it's asking for you for T after 4 years. What does this look like? You don't have to write this out, the A to the T, but sometimes people like to. I'm starting with $3,000. And since it's continuously compounded, it's E raised to your rate, so in this case 0.05 times the years, 4. If you plug that all into your calculator, you should get that it is a 3,664. I want you to answer the second one. How much would be in that account after 4 years of high school by yourself? And there you go. That's it for 7.2. Thank you for joining me, and have a great, grand, wonderful day.